In this video, I'm going to go over the procedure for how to solve logarithmic inequalities. So let's get started right away. Let's quickly review how to solve inequality for polynomials, like a quadratic inequality, okay? In general, it's easier, I should say, to solve inequalities when we compare with zero. Why do we want to compare with zero? Because we're just basically determining if it's positive or negative. Okay? So if we want to solve this inequality over here, x squared minus 3x is greater than 4, what we want to do is we want to set it to greater than or less than. So it's like setting it equal to 0, but instead here's the inequality sign. Okay, so let's move this 4 on this left-hand side. So we subtract 4 on both sides. And then the left-hand side we can factor as x minus 4, x plus 1. Okay, from here we pick out the critical points, which is when this polynomial, this quadratic in this case, is 0. So when is it equal to 0? We use the zero product property. X is 4 or x is negative 1, okay? So we draw a number line. Some teachers require you to write a table. Number line is more visually easy to understand. So let's draw a number line with the two critical points, negative 1 and 4, okay? We remember that the value of y, that we consider this as y, is 0 at these two critical points. So we just need to check nearby or around it. Is it positive or negative? Okay, so again, the concept is these critical points are 0. So around it, it's either positive, greater than 0, or negative, which is less than 0. Cannot be 0 again, because these two are the points when it's 0. Okay, that's the whole idea for comparing with 0. Okay, so in this interval over here from negative infinity to negative 1, we can plug in any point there. For example, x is negative 2 is a nice point to plug in. We can plug into right here. If we do, we get negative number times a negative number, two negatives make a positive. In this middle interval, we can plug in like x is 0. We would get negative 4 times 1, which is negative. Okay, y is negative. And in this interval, we can plug in x is, most people would probably plug in x is 5. You can plug in x is 10. Make it extreme for yourself because this will for sure be positive, and this will for sure be positive. So two positives make a positive. Two positives be multiplied to each other. Okay. So what are we interested in? We're interested in when it's greater than 0. So it's in this interval over here and this interval over here. So x is less than negative 1, or x is greater than 4, which in interval notation, we write it as negative infinity to negative 1, union 4 to infinity. Okay. All right, with that review, now let's go into some simple examples. Let's go into the simplest example, actually, of solving this logarithmic inequality. So if we want to solve log base 2 of x is greater than 0, well, of course, we could just look at the graph, but I'm going to explain the graph, and then we'll build the framework to solve these inequalities, more complicated inequalities, okay? So when is the log greater than or equal, sorry, when is it equal to 0, first of all? Log of any base. It's when x is equal to 1. Okay, and then we recall that log monotonically increases. It keeps increasing, yeah? So after this point, when it crosses 0, it's always going to be positive. And before this point where it crosses 0, it's always negative. Okay, so in this case, we're interested when it's positive. So it's when x is greater than 1. That's the solution to this inequality. So this builds the framework. Because we recall that log of 1 is 0, log of any base, log of 1 is 0, we can just set the argument of the log, which means what's in the parentheses, greater than 1. That's our algorithm. Okay, so let's do the next example, which is just a variation of that one. So ln of x minus 2 greater than or equal to 0. We want to solve this inequality. So what do we do? Our algorithm we just made up. We set the argument of the log, which is x minus 2, greater than or equal to 1. Why do we do that again? Because log of 1 is 0. So in this case, we're interested when the log is positive. So after that point where it crosses 0, it's always positive. So we set the argument of the log greater than or equal to 1. Okay, and we solve for x. X is greater than or equal to 3. So in the remote notation, It's 3 with the square bracket to infinity with parentheses. Okay, and if we check example 2, we know that ln of x minus 2 is a natural log shifted to the right by 2. So we confirm that it's positive when x is greater than or equal to 3, greater than or equal to 0, so we include when it's 0. Okay. All right, next one. It's also simple, but I added a trick to build the momentum. Okay. So we want to solve this inequality, natural log of minus x plus 1 over 2 less than 0. Okay, so the log is negative when the argument is less than 1. Okay, so we set this guy less than 1. We start solving for x, multiply by 2 on both sides, and then I subtracted 1 on both sides, and then I multiplied by negative 1 on both sides. So we flip the inequality sign because we're multiplying by a negative. So x is greater than negative 1. Okay, so if we think that's the answer, we have to be careful because that's not right. Let's graph this guy, ln of minus x plus 1 over 2. Look, looks like this. Okay, and we're saying that the solution is x is greater than negative 1, which is kind of true, but notice there's an asymptote going on probably at x is 1 in the graph, yeah? So we can't include like x is 2, x is 3, because it's not on the graph. And why is that? It's because of the domain. We must consider the original domain. What was the domain of ln of minus x plus 1 over 2? We set the argument greater than 0. So we get that x is less than 1, which confirms what we're seeing, this vertical asymptote at x is equal to 1. Yeah? So we got to modify our solution. It is when x is greater than negative 1, but it's also when x is less than 1. So when we combine those two, what do we get? We get parentheses, negative 1, comma, 1, close the parentheses. Okay. So in this example, we learned that we have to consider the domain as well. In these cases, I didn't bother going over it because we didn't have an issue. Okay. But in general, we have to consider the domain. All right, so now let's go over some more intermediate examples with that domain comment in mind now. So let's solve this inequality, ln of x plus ln of x minus 3 greater than ln of 4. Okay, so in order to use our previous algorithms, we want to set it greater than 0 or less than 0. So we got to move everything to one side. So let's minus ln of 4 on both sides. That's this line right here. And now let's start combining the logs because we want log of something is greater than 0 so that we can set that something greater than 1, right? So ln A plus ln B is ln of A times B. That's right there. And ln A minus ln B is ln of A over B right here. Okay, so now when we combine the logs, we set the argument greater than 1 because we want the output of the log positive. Okay, so we get x times x minus 3 over 4 less than 1. Multiply by 4 on both sides, and I distributed this x to both those terms. So x squared minus 3x is greater than 4. All right, so this guy, we continue solving. Actually, this is the exact same inequality as it was in the review up here. Yeah, so we already have the solution. It is negative infinity to negative 1, union 4 to infinity. Okay, let me go back to there now. Where was I? I was here. Okay. So we arrived here, and then as I said, we already solved it. It's this guy. So now let's consider the domain. What was the original domain of this guy over here? Well, ln x, the domain is x is greater than 0. ln of x minus 3, the domain is x is greater than 3. Which one's more restrictive? X is greater than 3, yeah? Because you can't have x is 1 or 2, stuff like that, right? That would violate this domain, but it's fine for this guy. Okay, and ln 4 is just a constant, so we don't have to worry about that. The domain is all real numbers, okay? So the most restrictive one is x is greater than 3. So let's consider x is greater than 3 and this solution over here. Well, this over here, 4 to infinity, is even more restrictive, yeah? So this is the final answer. The final solution is 4 to infinity. You can even draw a number line to convince yourself of this being the most restrictive. Okay, I didn't do it here, but you could definitely do that on your own. Okay, let's do some post-analysis of what we just did. Okay. Because I borrowed the solution from earlier, it was quite quick. But if you had to do it by hand, you would have to test 3 points over here. Okay. However, this is why we're doing a post analysis that we can possibly improve the next time. If we had considered the domain, remember the domain was x is greater than 3 originally. So again, this was the original 3 points that you had to test because you did not consider the domain. But look, if we considered x is greater than 3, right here, it's in the middle of the, not in the middle per se, but it's within the middle interval, yeah? Excuse me, we can cut off everything less than 3 because it's not in the domain. So you could test 2 points instead. You can get rid of this point over here, this test point over here. So you can plug in x is 3.5 and x is 5. Technically, you couldn't plug in, I think we plugged in x is 0 in the beginning, right? Technically, you can still plug it in because 0 is typically a nice number to plug in. And you just determine the sign of that quadratic. So you can still use it to help you out, but if that didn't make sense, that's okay. Okay, excuse me. Now let's also talk about an alternative method. Okay, so let's start from the beginning again. Let's make both sides one singular log. So the right-hand side's already one log. We're good. Let's combine these two on the left-hand side. ln A plus ln B is ln of A times B. Okay. Now, let's pretend it's like a equation. What do we do when it's equations? We can exponentiate both sides. So that's why I wrote over here e to the ln of that guy greater than e to the ln of 4. And let's think about the inequality sign. This might flip if we do an operation that changes the positive or negative sign. Yeah, like when we divide or multiply by a negative number. Exponentiation is always positive. Okay, think about it. It's always positive, so the inequality sign will not flip. Okay, and now with that in mind, we can just simplify this inequality to x times x minus 3 is greater than 4. And this is the exact same quadratic inequality as before. Everything else is the same. So the alternative method is we make both sides log of something. And then we can kind of get rid of just the log because we exponentiate both sides. Okay. Last example. Let's solve this inequality. Log of x plus 2 plus log of x plus 1 less than log of 5x plus 1. So let's use the alternative method I just presented. Let's combine these two on the left-hand side to 1. So we will multiply the arguments. So it'll be x squared plus 3x plus 2. Okay, right-hand side remains the same. Exponentiate both sides. So we get x squared plus 3x plus 2 less than 5x plus 1. Okay, and if we move everything to one side, we get x squared minus 2x plus 1 less than 0. And we can factor the left-hand side to x minus 1 squared is less than 0. Okay, so now let's solve this inequality. If we remember how the graph looks, this is just y equals x squared shifted to the right by 1. Okay, it touches 0, but it never goes negative. So there's no solution. And we can confirm by plugging in test points. Okay. Therefore, this inequality has no solution. Okay, remember, it's possible that inequalities have no solutions. But here's an example in which this will never be true. So no solution. All right. Hopefully this was helpful. Hopefully this covered a vast variety of different cases. And hopefully the algorithm I presented and the alternative algorithm made sense and you can utilize it.